In the late 20th century, South Africa found itself at a crossroads in the development of armored warfare. The nation had long relied on imported British Centurion tanks, later upgraded and rebranded locally as the Oliphant series, to maintain its armored capabilities. While these upgrades had served effectively through the years, by the 1980s and 1990s the changing face of modern warfare revealed a critical gap. Around the world, armored forces were moving toward tanks with advanced fire control systems, powerful smoothbore guns, and enhanced armor protection capable of withstanding the most lethal anti-tank weapons of the era. For South Africa, maintaining a credible defense industry and ensuring that the South African National Defence Force (SANDF) would not fall behind technologically became a national security priority. This backdrop gave birth to the ambitious project known as the Tank Technology Demonstrator (TTD). The TTD was not simply conceived as another tank upgrade. It was envisioned as a revolutionary platform, a testbed to showcase what South African engineers and defense industries could achieve if given the freedom, resources, and vision to innovate. Unlike incremental modernization programs, the TTD was meant to stand shoulder to shoulder with the latest main battle tanks, MBTs, emerging from Europe, the United States, and even the Soviet Union at the time. In particular, comparisons were drawn with tanks such as the Leopard II, M1 Abrams, and Challenger II, all of which were becoming benchmarks of 20th-century armored superiority. The project emerged during an era of transition. The end of the Cold War reshaped global defense priorities, and in South Africa, political transformation meant new considerations for defense spending. Yet, within this uncertainty, the TTD offered something bold: the possibility of establishing South Africa not just as a consumer of military hardware, but as a designer of world-class armored systems. The Defense Research Unit and Armscor, the Armaments Corporation of South Africa, were heavily involved in the planning, drawing expertise from engineers who had decades of experience modifying the Oliphant and adapting technology under embargo conditions during apartheid. One of the unique aspects of the TTD project was the philosophy behind it. It was not intended for mass production from the start. Rather, it was a prototype, a demonstrator platform where the latest ideas in mobility, firepower, and survivability could be tested. If successful, the TTD could either evolve into a full-scale South African main battle tank, or at the very least, serve as a technological feeder program, contributing innovations to future armored vehicle projects. The chassis was built larger and heavier than the Oliphant, bringing the vehicle's combat weight to around 58 tons. Despite this weight, it was designed with remarkable agility in mind. A powerful twin-turbocharged diesel engine generating over 1,200 horsepower gave it a power-to-weight ratio of about 21 horsepower per ton, which was highly competitive with global MBTs of the time. With a top road speed of about 71 km per hour and impressive cross-country mobility, the TTD was no sluggish heavyweight. This mobility was essential for South African battle doctrine, which emphasized rapid maneuvering across vast terrains, from desert expanses to rugged savannas. Firepower was at the heart of the TTD vision. The prototype was initially fitted with a 105mm rifled gun for testing purposes, derived from South Africa's own developments and experience with British ordnance. However, the production version was planned to carry a 120mm smoothbore gun, a weapon system capable of firing modern NATO standard kinetic energy penetrators and advanced heat rounds. Even more ambitious was the idea of upscaling to a 140mm smoothbore gun, a caliber that few countries at the time had attempted to integrate, giving the TTD a theoretical edge against the thickest armor of any potential adversary. Alongside its main gun, the TTD carried a coaxial 7.62mm machine gun for anti-infantry roles, with potential for additional armament options such as a roof-mounted heavy machine gun. But it was not just firepower that made the TTD stand out. The design integrated advanced armor protection, making it one of the most heavily shielded prototypes of its era. The frontal glasses had an effective thickness estimated at 750mm against kinetic threats, a remarkable figure for the time. Its modular composite armor was engineered to resist both APF-SDS penetrators and chemical energy threats like heat rounds from 125mm Soviet tank guns, which were among the most common battlefield threats of that period. The side armor was sufficient to defeat 23mm autocannon fire, while the roof was strengthened to withstand artillery airbursts, particularly from 155mm shells. These design features reflected a comprehensive understanding of modern threats, not only direct anti-tank fire but also the evolving role of precision artillery and top-attack munitions. Equally important was the attention to crew survivability. The TTD incorporated internal fire suppression systems, ammunition storage solutions to reduce catastrophic explosions, and a general layout aimed at keeping the crew as safe as possible in high-threat environments. This aligned with global trends, where the focus was increasingly shifting toward protecting not only the machine but also the soldiers inside it. By the mid-1990s, the TTD prototype was completed and demonstrated. Its imposing silhouette, with a wide turret, long barrel, and modern armored contours, made a strong impression. Test drives and limited demonstrations revealed its raw power and potential. Engineers and observers recognized it as a genuine competitor to the world's leading MBTs, proving that South Africa's defense industry had the talent and ingenuity to produce a top-tier armored fighting vehicle. However, as is often the case in defense projects, the reality of economics and politics intervened. While the TTD had proven its technical merits, the cost of serial production was deemed prohibitive. Post-apartheid South Africa faced pressing social and economic priorities, and defense spending was dramatically reduced. For policymakers, investing in a new, expensive tank program was difficult to justify, particularly when the Oliphant Mk2, a much cheaper modernization of existing Centurion hulls, could serve as an adequate solution for the SANDF's limited requirements. Thus, the TTD remained what its name implied, a technology demonstrator, a one-of-a-kind prototype preserved as a symbol of ambition rather than mass-produced reality. When analyzing the tank technology demonstrator TTD, one cannot help but marvel at the meticulous engineering that went into its construction. Every component, from the suspension to the fire control system, was a reflection of lessons learned through decades of South African armored operations in hostile environments. Unlike European or North American tanks, which were designed primarily for large-scale conventional warfare in temperate regions, South African armor had to be adapted to fight in deserts, savannas, and mountainous terrain. The TTD therefore represents a fascinating blend of global armored warfare doctrine and uniquely African battlefield experience. Mobility and suspension design. Mobility was a cornerstone of the TTD's design philosophy. South African engineers understood that a tank which cannot maneuver effectively is a liability, no matter how strong its gun or armor might be. To this end, the TTD incorporated a powerful twin-turbocharged V8 diesel engine producing approximately 1,234 horsepower. With a combat weight of about 58 tons, this gave the tank an impressive power-to-weight ratio of more than 21 horsepower/ton, enabling it to achieve speeds up to 71 km/h on roads. Off-road, its performance remained competitive, capable of sustaining around 35 km/h across rough terrain. The torsion bar suspension, enhanced with hydraulic dampers, offered a balance between durability and ride comfort. This was essential not only for crew endurance but also for firing accuracy on the move. The suspension was engineered to handle South Africa's harsh environments, which include sand dunes, rocky outcrops, and mud plains. Such conditions often challenge even the most advanced armored vehicles, but the TTD was built with the versatility to maintain operational tempo in these landscapes. Firepower and armament potential. While the prototype carried a 105mm GT3 rifled gun for testing, the true ambition lay in the planned transition to a 120mm smoothbore gun. This would have placed the TTD in the same league as tanks like the German Leopard 2 and the American M1A1 Abrams, both of which were defining NATO standards during the 1980s and 1990s. The 120mm gun offered compatibility with a wide range of NATO munitions, including armor-piercing fin-stabilized discarding Sabot APF-SDS rounds and high-explosive anti-tank PEEP shells. More ambitious still was the proposal to mount a 140mm smoothbore gun, a caliber only experimented with by a handful of nations. A weapon of this size promised unrivaled penetration capability against even the heaviest armor. Had the TTD achieved this armament upgrade, it would have been one of the most powerful tank guns in existence, surpassing its Western contemporaries. However, the 140mm gun posed logistical and engineering challenges, including recoil management and ammunition storage, which would have required extensive redesigns. Supporting this primary weapon was a coaxial 7.62mm Browning machine gun, effective against infantry and light vehicles. The potential existed for a roof-mounted heavy machine gun or automatic grenade launcher, though the prototype configuration remained relatively modest in secondary armament. Armor and protection. Perhaps the most impressive element of the TTD was its protection. The frontal armor was estimated to provide an effective thickness of about 750 mm, capable of defeating 125 mm APF-SDS and heat rounds, the mainstay of Soviet tank armament at the time. This level of defense placed the TTD firmly in the same category as the Challenger 2 and Abrams, both of which emphasized crew survivability through heavy frontal armor arrays. The armor was composite, with spaced layers and modular sections that could be upgraded or replaced depending on the threat environment. This modular philosophy foreshadowed trends in later 21st century armored vehicle design, where adaptability became essential in addressing rapidly evolving anti-tank weaponry. Side armor protection was robust enough to withstand hits from 23mm autocannons, weapons commonly mounted on infantry fighting vehicles and attack aircraft. The roof armor, often a weak point in tank design, was reinforced to resist airburst artillery strikes, particularly from 155mm shells. Considering the increasing prevalence of top attack munitions and cluster sub-munitions in modern warfare, this was a forward-thinking feature. In addition to passive protection, engineers had considered adding explosive reactive armor era packages to enhance survivability against chemical energy penetrators. While not integrated on the prototype, the TTD had the design flexibility to accept such upgrades. Fire control and electronics. Though the TTD did not reach mass production, reports suggest it was designed with an advanced fire control system, incorporating thermal imaging, laser rangefinding, and stabilized optics. These systems would have allowed the tank to engage targets accurately while on the move, day or night, and in poor weather conditions. Such capabilities were becoming the global standard by the late 20th century, and South Africa was determined not to be left behind. Comparison with contemporary tanks. When compared against its international peers, the TTD demonstrates both strengths and limitations. Versus the Leopard 2, the TTD's mobility and potential 120mm gun put it on par with the Leopard 2, though Germany's tank enjoyed stronger logistical backing and a proven production line. Versus the M1 Abrams. The Abrams benefited from advanced Chobham armor and a gas turbine engine, giving it different performance characteristics. The TTD's diesel design, however, was more fuel efficient, a vital consideration in extended African operations. Versus the Challenger 2. In terms of protection, the TTD's frontal armor was competitive, though the Challenger 2's rifled 120mm gun provided different firing characteristics. Versus Soviet MBT's T-72, T-80, the TTD would have had a significant advantage in armor protection and fire control, while its planned 120mm or 140mm armament would likely have outgunned standard Soviet tank guns. Engineering innovations. The TTD introduced several innovations that, while not mass-produced, demonstrated South Africa's technical creativity. These included 1. High power-to-weight ratio, ensuring agility despite its heavy protection. 2. Advanced composite armor, designed indigenously to resist a wide spectrum of threats. 3. Modular upgrade philosophy, anticipating the need to adapt to future battlefield technologies. 4. Potential for 140mm armament, pushing the limits of global tank design at the time. 5. Adaptability for harsh terrain, unique to South Africa's operational environment. These innovations proved that the nation's defense industry, though smaller than that of Western powers, was capable of competing at the highest levels of armored design. Symbolism of the TTD. Beyond its technical attributes, the TTD carried symbolic weight. It was a declaration that South Africa, despite decades of isolation under international embargoes, could stand on its own technologically. It represented self-reliance, resilience, and ambition. In the post-apartheid era, when the country was redefining its identity on the world stage, the TTD also highlighted the tension between global integration and domestic priorities. Should South Africa spend billions developing its own tanks, or should it focus on socio-economic challenges at home? The shelving of the TTD answered that question, but the prototype remains a symbol of what could have been.